Physics technology used in Voyager 1 space probe.
So the reason we chose to do Voyager project was because it's a very interesting project that covers a large variety of physics concepts such as wavelength, frequency, and optics. Although there were things we couldn't go into due to our limited understanding as grade 10 students, we still found the topic very interesting indeed.
So the Voyager spacecraft is a spacecraft designed by NASA in hopes of finding and collecting information on Jupiter, Saturn, and other planets and other astronomical objects within the solar system. Yet as they succeeded, the missions were changed to even bigger ones, like exploring the universe, not literally though. So the Voyager 1 and 2 path. Voyager 1 and 2 were built in the late 1970s to take advantage of a rare geometric alignment of 4 planets in the solar system. If all the planets were all arranged in a straight line, then the Voyagers can explore all the planets while spending minimal fuel, resources, and time. So the initial launch. The Voyagers were built and launched from Cape Canaveral, Florida in 1977.
Okay, as Voyager was an old probe, it was actually equipped with the best of the best technology back then. As we delve into it in this slide, we will only talk about the ones that are interesting since there are that many and they're really, really complex as well as time consuming. So bus. So bus housing electronics. It is the base structure of the spacecraft. A 10-sided box, as you can tell on the picture shown. The center line of the box is called the Z-axis, and the high gain antenna is pointing towards the Earth. While the spacecraft is designed to roll according to the axis, it's actually from the direction of Earth. So from people who are on Earth looking at it, it is done by small thrusters attached to the buses on the sides. Each slide contains a bay which houses electronic assemblies numbered clockwise. By one count, maybe bay 1 containing the radio transmitters and bay 2 might contain cosmic ray subsystems, etc. Cosmic ray systems. So CRS looks for very energetic particles in plasma. Also has the highest sensitivity of all three particle detectors. Energetic particles can be found in the high-intense radiation fields surrounding planets. Particles known as highest energy comes from other stars. CRS does not capture or slow the energized particles. They pass completely through it. But because it has passed through it, the particles will leave a trace of their existence. It is used to measure particle charge composition in the magnetosphere of different planets, measuring 3D streaming patterns of nuclei in hydrogen through iron and electron over long range. It is also used to provide information on energy content, origin, and acceleration process, life history, and dynamics of cosmic rays in the galaxy.
So the ultraviolet spectrometer is a special kind of light meter that is sensitive to ultraviolet light. Basically, its job is to determine the proper exposure for a photograph that the Voyager will take. So what does this mean? Well, the sun emits a large range of colors of light. To put it simply, the sunlight passes through an atmosphere. The spectrometer detects the UV rays and sort of filters out the unwanted colors in order to take the photograph. The ultraviolet spectrometer covers the wavelength range of 40 nanometers to 180 nanometers. So this is the Imaging Science Subsystem, also known as the ISS. The photos taken by Voyager spacecrafts have given humanity new insight into the planets and other objects of our solar system. So how do Voyager 1 and 2 take photos? Well, the Image Science Subsystem is a camera system the Voyager took photos with. It consists of 2 different cameras. a wide-angle camera and a narrow-angle camera. The wide-angle camera is used to capture broad images, as the wide views of Saturn. The narrow-angle camera, on the other hand, is used to capture higher resolution images of smaller objects, such as Jupiter's storm, craters, asteroids, and other small astronomical objects. The wide-angle camera uses lenses, while the narrow-angle camera uses mirrors to focus light. Peter Thomas, a planetary scientist for Cornell University, said that the cameras were built to withstand over 10 years the harsh conditions of outer space. The whole system weighs approximately 58 kilograms. Now, unfortunately, after the camera systems for the Voyager spacecraft had taken many great and informative photos, they were shut down in 1990 in order to conserve energy and power for the spacecraft.
So the iris, or infrared, interferometer, spectrometer, and radiometer. It actually has 3 parts to it. First off, the interferometer determines the distribution of heat energy a body is emitting, which in turn allows us to know the temperature. Second, it has a device which allows us to know what elements are present on the atmosphere or on a surface. And third, the radiometer measures the total sunlight reflected by a body at UV, visible spectrum, and infrared frequencies. So sadly, there are no visuals for optical calibration target. So the target plate has colors and brightness pre-recorded. So when the target is been scanned by the cameras, the information relayed will be seen by the scientists to see if there's actual accuracy or if it needs calibration. Photopolarimeter subsystems. This is going to be a long one. So it has a 0.2 millimeter telescope equipped with filters and polarization analyzer. It covers from 235 nanometers to 750 nanometers. It was also an experiment to determine the physical properties of particulate matter on different planets, as well as different rings and moons of the planets. The experiment is a bit more complex, so we won't delve into the details, and yes. Radioisotope thermoelectric generator. The 3 radioisotopic thermoelectric generators are electrically parallel connected, as seen in the diagram here. There are the central power source, which has a radioisotope heat source, a thermal electric converter, and a gas pressure venting system, temperature transconductor, connectors, a heat injecting cylindrical container. The energy source used is plutonium-238 in the form of the oxide PuO2.
So, how does the Voyager 1 communicate with Earth while it's 21 billion kilometers away? Well, the Deep Space Network works in tandem with the high-gain antenna in order to communicate information to and from the Voyager spacecrafts. The Deep Space Network is a network of radio antennas located in California. The high-gain antenna is an antenna on the Voyager 1 that communicated with the Deep Space Network. The Deep Space Network, or DSN, was invented in 1963 by William H. Pickering. So the Deep Space Network and the high-gain antenna work very much the same way satellite dishes work. They are shaped like a convex lens. When radio signals hit the surface of the antenna parallel to the principal axis, it reflects back towards the focal point of the satellite where the radio signal is picked up, as shown in the diagram. Sending signals is the exact opposite process of receiving signals. We are able to communicate with Voyager 1 using this method, even when it is 21 billion kilometers away from us.
So here we'll cover some general contributions by Voyager 1 and a little by Voyager 2 as well. So Voyager 1, interstellar space in August of 2012, nearly 35 years after blasting off. Scientists announced that Voyager 1's declining power supply will have to force the mission team to turn off a lot of its instruments in 2020, and all of the science gear will stop working by 2025. The Voyager spacecrafts are the third and fourth spacecraft to leave Earth orbit on February 17th, 1998. The Voyager 1 proceeds to pass over the Pioneers and thus becoming the furthest known invention in space from Earth. So the contributions to society. Voyager 1 twins, Voyager 1 and 2, are the first two probes to go the furthest distance from Earth, and Voyager 1 was the first one to explore into interstellar space. Traveling into interstellar space, it is now 21.2 billion kilometers away from Earth as of today. As for what it contains the proof of humanity really existed, the golden records. The golden records are to show pictures, music, and readings and writings that were the best parts of humanity. It also has information on the story of a world for any future finders of the disk. As for exploration, it helped us into our solar system. Voyager 1 was the first one to explore the giants and take good pictures, like really good pictures of Jupiter and Saturn. We also learned that there were 2 new rings as well as 11 new moons that were discovered on Uranus by Voyager 2, which is the twin of the Voyager twins. It's known that it is known that there's actually a new finding on Uranus, which is a leak in the atmosphere on Uranus, and resulting in a really astounding topic that the scientists are trying to cover in recent days. So the interstellar mission was added on after original flybys of the first two planets were so successful. It happened because they realized that it was already far enough into space and that nothing had gone wrong, and they were actually only like 20% of fuel down after traveling to a third planet, and then so they decided to continue the search into interstellar space. The mission, it is really effective, actually, indeed. The two probes were launched into space with the best technology at that time, said previously. They were actually still pretty relevant as of today. If we were to use it, it would be around the pictures would be around 840 frames pixels, and then it uses different types of filters to show different types of colors. Each picture is actually taken multiple times with a different filter so that the colors like RGB or YMCK are shown onto the thing. The mission of it right now is to extend humanity's, it's basically becoming a time capsule for humanity. So optics. It uses Vidicon tubes, which is why it's so freaking relevant as of today. It's pretty overpowered. As you can tell from this diagram here, they are the main source of pictures back in the 1970s, as well as the Vidicon tube uses a photoconductive surface to capture all the images they use. So photoconductivity, it is the tendency of a substance to conduct electricity depending on the intensity of the light. Photoconductive surfaces are usually made of germanium, gallium, selenium, or silicon, and sometimes they actually use different types of metal oxides in replacement of that. So in English, photoconductivity is how much the electric current is increased when sufficient energy is presented. So onto the history, tiny history, not a lot of history on this actually, because the Vidicon 2 was soon replaced with different other types since it was pretty it actually took 50 years for it to actually properly develop as a tube, as like the video conductor tube. So it was invented in 1924, and well, the theory was passed in 1924, and the real development happened in the 1950s. In 1970, it was NASA or JPL, Jet Propulsion Laboratory in California, decided that if they were to upgrade the tube enough, it should be still relevant as of today, and it is still pretty relevant.
So this is how Voyager 1 is related to physics, not just in the optical field, but as well as many other fields, by Homin and Xi.
Main sources came from Voyager, obviously, because it's launched by NASA, and so most things were used from NASA from that exact webpage. Thank you for listening, and